So we'll start up again on the deglaciation, and we started looking at the CO2 changes and the orbital forcing of insolation. So remember now that it's the orbital forcing that is responsible for initiating the retreat of the glaciers, and then there are vegetation feedbacks, which we will see a little bit more, and of course ice albedo feedbacks. And the CO2 in this case is a response to deglaciation, and then it also feeds back to the change in temperatures, rate of deglaciation, and so on. So obviously that also results in sea level change, which we saw in terms of the C14 and thorium uranium ages. And there are now many more feedbacks, as I said, that will be of interest for global warming timescales. So the local meltwater pulses were recorded in the Gulf of Mexico and just north of the Arctic Circle to the east of Greenland. What are meltwater fluxes? Basically, if you have salty water, so Gulf of Mexico has a certain temperature, certain salinity, and if the glaciers that melted here released huge amounts of fresh water that flowed south into the Gulf of Mexico, they will create a change in temperature and salinity, which will be recorded in the delta O18 of the calcium carbonate shells in the ocean phytoplankton, zooplankton that live in the Gulf of Mexico or up here in the Arctic region. Okay, so those pulses are important. Why? Basically, they indicate two things. One, that there was a southward path of the meltwater flux, and there was also a eastward path of the meltwater flux. There is also a path this way, as we will see in a minute. You probably already can guess where I am going with it, because whenever we are in this region, we always think about North Atlantic deep water formation, which means how much evaporation is happening, how much deep water is forming, and if you change the air temperature or the salt content of the water, salinity of the water, what will happen to the amount of North Atlantic deep water that's being formed, what that will do to the meridional overturning circulation and the global thermohaline circulation, what they will do in terms of the amount of carbon dioxide going into the ocean, amount of heat going into the ocean. Remember, once it goes down, it stays there for hundreds to couple of thousand years. So that's very important. So we can see some of that here. This is now somewhat of a detailed figure, but we will go through carefully. First of all, this flower is called Dryas. It's a cold Arctic flower, and it grows when the temperatures are below a certain threshold, and we will see that it provided a critical indication of how the deglaciation had some hiccups as we were coming out of the last ice age. So here it is showing the fronts. The glacial polar front came all the way to here when the last ice age was at its maximum 20,000 years ago. As it started to melt, the front began to retreat towards the pole, but you can see that as it retreated to some latitude and longitude up here, suddenly there was a reversal and a recooling or a refreezing happened, and then it began to retreat again. So there is a period called the Younger Dryas, which was a refreezing. So the deglaciation started 20,000 years ago, kept on going till about 12,000 years, and suddenly something happened and there was a reversal, and the ice glaciers started to rebuild. The global temperatures dropped. At least there is strong evidence that it dropped in the northern hemisphere. There is also some evidence that it dropped in the southern hemisphere. The stronger cooling was in the northern hemisphere. So let's look at it with these various evidences. Here is the depth of a sediment core, and here is depth of some pollen found in another sediment core, and these are years dated with some geotracer like C14. So what are we looking at? Basically, if you look at the polar Foraminifera, it's a kind of plankton species that grows in cold polar waters. As deglaciation started happening, it was beginning to decrease. So look at the scale here, okay, be careful. It is going from 0 to 100% here. So if you were close to 100% when the glaciation was occurring, cold polar waters were all the way down into lower latitudes. As the glacier began to melt, the percentage of polar Foraminifera in core taken somewhere in the south This one particularly was found in the polar waters in the North Atlantic. It began to drop and it kind of remained at that stage, had a little hiccup. So every time it went in this direction means the polar Foraminifera increased in the percentage in the sediment, which means colder waters were re-established. So the warming started, the percentage of polar Foraminifera began to decrease, but there was then one huge burst during about 12,000 years, as we will see here. So here it is just before we hit 12,000 years, and that huge pulse here was also associated with cooling on land. As you can see here, the tree pollen began to increase, and then it remained at some level, and then it seems to recover and then come back. So essentially the temperatures began to warm, something happened, large scale cooling happened again for a short time, and then it went back to warming and the deglaciation got completed after that. So what can cause such rapid changes? Why do I say rapid? We will see in a minute that some of these changes happened in 3 years, 10 years, 100 years and so on. That makes the time scale very important to understand, because if there are things in the global climate system that can change on such an abrupt time scale, in the human life in a societal level, 3 to 10 years is a very short time. If you have a big change that happens in 3 to 10 years, it can cause a lot of disruptions to human life, economic activities, infrastructure, coastal life, etc., right? So here it is. So deglaciation started, the estimated temperatures are up here, started to warm, then somehow slow cooling began, and then there was a big pulse of cooling before the warming recovered. So I pointed out two things, this younger Dryas and rapid cooling, and I also showed freshwater pulses in various places, and you can begin to imagine that this must have had something to do with that. So now look at some more evidence in terms of ice accumulation collected from various evidences like wind-blown dust, calcium in the dust and so on. And you can see that at late glacial, here is the ice accumulation rates. It seems to be decreasing, and suddenly ice accumulation rate increases. So it jumps from about 0.1 to 0.2 meters per year. You have to kind of get a sense of how big that is. Okay? So when we do ice albedo feedbacks in more detail, we will come back to that. Okay? I kept saying that there is an asymmetry when the glacier is melting and versus when glacier is growing. So when glacier grows and the temperatures are cooling, the amount of water keeps reducing in the atmosphere because cold air holds much less moisture. So 0.1 meter per year is a significant rate. If you jump to 0.2 meters, that means doubling of the growth of the ice. So there is plenty of cooling associated in making such a big jump in growth of ice accumulation by that much. So here you are in about 100 years, a huge jump from 0.1 meter per year to 0.2 meter per year, and this whole period, especially this jump here, you can see on the left side here, has pulses of 3 to 10 years. So this ice core data is so good that you can actually get time scales of few years. So within 100 years you had multiple jumps back and forth. So if there is really any feedback in the system that can produce such large pulses in ice growth and ice melting, that is something we should be aware of, and we should figure out exactly what processes cause such big jumps. And you can see that also when glaciation happens, we know that the dry weather increases, rainfall reduces, there is more dust. Ice also scrapes up dust and produces fine silt, which then is taken away by air and deposited in various places. So every time there is a jump in dust concentration, it typically corresponds to increased glaciation and cooling. So when we looked at ice core, they actually measure conductivity along the ice core, and the dust particles in the ice change the conductivity of the ice core. So the dust concentration like this can be measured by changing the conductivity of the ice core. Again, additional evidence, but also with details of time scales which are very critical for global warming feedbacks. So let's get a bit more into the details of the processes then. So here is the approximate outline of the extent of the glacier at the last glacial maximum. As the glacier behind started to melt, a lot of these bays and lakes and so on got filled up, plus whatever excess water was there started to flow down into the Gulf of Mexico and out into the Arctic Ocean and the Labrador Sea. So it so happened that one of the lakes here, called the Lake Agassiz, filled up, but some part of the ice remained unbroken. The melting is not always uniform because of the mountain height of the mountain or the depth of the valley and so on. The heating rates can be very different. The ice albedo feedbacks can be locally very different. So you can get big melts in one place and slow melts in other places. So at some point that ice dam broke, and a huge pulse of water that was dammed behind that ice bridge rushed into the Labrador Sea and the Greenland, Iceland, Norwegian seas. And you can imagine what happens if you put substantial amount of fresh water in that region. You are essentially going to reduce the density of the water so much that for the same amount of evaporation, you will not be able to produce as much deep water. And if that water doesn't sink, you don't bring as much warm water north with the current Gulf Stream. We didn't explicitly say Gulf Stream so far, but we will see it again. So there is this warm western boundary current that comes up. It doesn't come this far up, goes off this way. This projection is a little bit strange, so you have to be careful. So that circulation change is going to allow the whole system to refreeze. The best example I can give you is a movie called Day After Tomorrow. I don't know if you have seen it. If you have not, you can check it out. Essentially, the movie starts by reporting that they are observing ocean temperatures that are 14 degrees warmer than normal, and then before you know it, there is glaciers growing in New York City. How does that happen? Essentially, the idea is the same, that if lot of warming happens and lots of glacier from Greenland melts, and or in this case from the Laurentide ice sheet which was on North America, and if they release lot of freshwater pulse, that would perturb the meridional overturning circulation, the heat transport, and basically change the climate very abruptly. Okay, in this case things happened in 3 to 10 year time scales. So that's something we must be aware of. Of course, there were carbon dioxide feedbacks. So here is the sea level that we looked at before, about 120 meters. We said we went from 120 meters below current levels to about the current levels, and we already said several times that the carbon dioxide changes by 80 to 100 ppm from a glacial period to a deglacial or interglacial period. So you can see that there is a coherent increase, even though there are some flattenings of CO2 increase, and here we are essentially in the so-called Holocene. So we will come back to some details of the Holocenes when we look at the millennial timescale climate change, but this re-emphasizes the fact that carbon dioxide always comes back to play a role in climate change. We must keep emphasizing again and again, because this is what we are changing right now with human activities, fossil fuel burning, deforestation, and so on and so forth. Okay, so this is showing basically the map of deglacial flooding coastlines, which means which were the coasts that were exposed because of the drop in sea level when there were these huge Laurentide and Eurasian glaciers. So you can see that all the way down to Australia, New Zealand, tip of South America and Africa and so on, and of course into the northern hemisphere like the Bering Strait, etc. These are where land was exposed because of drop in sea level. If you drop the sea level by 120 meters, obviously you are going to expose a lot of the shelf, and these are all the exposed shelf areas because of freezing up a lot of the water in the glacier. So you can imagine that by this time, 20,000 years to now, lots of human migrations, animal migrations, etc. have happened. So many times we don't know exactly how some species got to where they are, but these levels of changes in sea level will create new land bridges. For example, here you would have gone from the Eurasian subcontinent into North American continent. So you can imagine that the migration would go all the way into South America, and there is in fact evidence that a lot of the animals, megafauna, so-called megafauna, etc., traversed all the way into these continents. So these changes, and we still don't know, for example, the timelines of the migration of our ancestors from here all the way into Australia and even some remote islands of Polynesia and Melanesia and so on and so forth. So it's always interesting to know how ice ages, sea level changes have motivated such migrations, because not only are there new opportunities to travel to places across these exposed land bridges, but the changes in weather. If you, for example, have a lot of glaciation here, you would have caused lots of climate change over here. Cooling means usually crop loss. So if you were depending on some forest for food, and if that forest begins to degrade because of cold weather, then you are going to start to look for new places to live in, and so on. So all migrations have some component of climate in addition to maybe just the inherent curiosity of our ancestors to move around. That's why the human migration and climate change then begin to interact with each other on all sorts of time scales as well. So going back to then our favorite diagram of showing the radiation change in the summer, winter, CO2 change and ice change, let's focus on this period, which is essentially now the end of the glaciation. It's completed. So now we can look at how the tropical climate began to change, which obviously brings us back to the monsoon. So you can see now that the glaciation has ended, but the summer insolation is beginning to drop. So the entire Holocene and human activity and deforestation, agriculture, etc., have been happening in a substantial change in the summer insolation. So technically we were continuing that 50 million year cooling. So the question then, of course, in the global warming context is, were we headed into a next ice age? If so, how is human activity and global warming changing the arrival of the next ice age? So we'll see in a minute what orbital changes are coming in the next few thousand years. Using the Milankovitch calculations, we can easily say how the precession change, obliquity change are going to change the insolation in the coming years, centuries, decades, millennia, whatever, right? So here are the observations of effective moisture 9,000 years ago compared to today. So now we are getting into human historic period, right? By this time, all our ancestors, Homo erectus, Homo habilis, Neanderthals, everybody has disappeared, and only Homo sapiens are remaining. So this is the time where there is plenty of historic record to show that when the North Africa was greener, lots of lakes were full of water, soil moisture was higher, agriculture was possible. Lots of civilizations began to expand from the basic Nile basin across all of Africa. So we are now getting really into human history. So it's not anymore just theoretical interest. We need to understand how climate has affected our evolution in the last 10,000 years. And the same thing over here. The Indus Valley civilizations, Chinese and other civilizations over here, they are all beginning to have more moisture, more agriculture possible, expansion of civilizations. Essentially, I will digress a little bit and point out that when agriculture became a mode of life as opposed to the hunter-gatherer lifestyle before, so if you go all the way back to the so-called Paleolithic, which starts a couple of million years ago and extends into about 15,000 years, and then we have the so-called Mesolithic and Neolithic periods, the Stone Ages. Then when we went from being hunter-gatherers to agricultural society, we began to stay in one place, grow crops, domesticate wild grasses like wheat and rice and so on. And then once people settled down, the communities began to get larger. There are evidences that when they were not moving around too much, the fertility rates went up, the family structures changed, there were more people to take care of babies because we were settled in one place instead of moving around. And all these kind of anthropologic factors played into the explosion of population. So population also began to grow tremendously from this time when there was large scale greening coming out of the last glacial maximum into the deglacial period. So human population itself changed. That itself began to feed back into climate by changing vegetation and so on. And this is relevant because as we project into the future, one of the most critical things we have to worry about is how human population will change into the future. We will come back to that when we discuss more on global warming. So here is some evidence of changes in effective moisture. So wherever it is green, there was greater moisture 9,000 years ago. Wherever there is yellowish, there is less moisture, and all the other regions, they are similar to what is available today. This is from the observations. This is from the model simulation. So why is the model continent looking bizarre? Now you have to use your knowledge of how the models use grid boxes. So if you have a map like this in a continuous projection, when the models make a grid, they have 500-kilometer grid, so they will end up putting boxes like this. So the continent look very boxy. Okay, as we increase the resolution or decrease the grid size, then they will become more and more realistic looking compared to the real map. Nonetheless, you can see that the Indian Asian monsoon began to get pretty much stronger than it is today. We had similar moisture levels back in 9,000 years ago, but this region where the Mohenjo-daro, Harappa and Indus Valley civilizations were was much wetter than it is now. So that explains some of why they might have had trouble as they went closer to the current period. And lots of expansions of civilizations over Africa, and you can see that in terms of the lake levels in Africa going from the present to 20,000 years ago, or coming from 20,000 years ago to the present. So you can see that 9,200 years ago to or so to the so-called climatic optimum in the Holocene, which we will see again later on when we come back to more recent millennial timescale climate change. And then it has dried again, and it has remained at this stage for last couple of thousand years. And these are model simulations of excess moisture, which means moisture surplus, which basically means precipitation compared to evaporation, and the models are able to reproduce evidences of past lake levels. So lake levels are reconstructed again by looking at various biogeochemical evidences in the sediments and so on and so forth. So we will see another nice map of how the populations expanded from the Nile River towards each direction and how they shrank back once this excess monsoon disappeared and the lake levels began to drop severely. Here is repeating some of the points, because we will add a little bit of detail to how the feedbacks happen when monsoon changes. So by this time we obviously have the Tibetan Plateau, and here is our classic southwest monsoon. I already pointed out that when you have along-shore winds like this, the winds will try to drag the water like this. Coriolis will push to the right, which means water is being pushed away from the coast near the surface. Every time you move water, new water has to come from somewhere. So in this case it will come from below, so that is upwelling. So you have upwelling and biological production signals, as well as speleothems in these regions and speleothems all over these places where rainfall change is recorded as thorium uranium signatures, which we can use to reconstruct things like this. The upwelling species began to increase because the monsoon got stronger to about 9,000 years, and then they have dropped to the current level because this monsoon wind is putting a signature in upwelling and hence biological production and hence the geochemical signatures in delta O18, calcium carbonate and so on. So, this again is important because as I said, with global warming we are expecting the land to warm faster than the ocean because of the heat capacity differences. But as I said, the dust and the pollution is actually not allowing the land to warm as fast. So, the monsoon is not getting stronger, in fact it has weakened. As I also mentioned, there is some evidence that maybe it is recovering, which means somehow maybe dust is reducing. So, we have to figure out why suddenly dust began to decrease. That is something to figure out. Plus, usually when a change happens, you cannot say within 1 or 2 years that, oh, change has happened. You typically have to wait for 10, 20 years to see if that is a real change or if that is just a year to year variability. So, the time scales always are kind of tricky. So, you have to wait long enough. But if you are getting drier and you wait too long, then obviously you have to, how do you adapt to the change? So, you have to rely on model projections and so on to see if the drying or the wetting process will continue or not. So, all those kinds of things have to be worried about. The other thing to worry about here is, so the modern summer monsoon picked up, you can see the latitudinal distribution here of rainfall, and with the model what you can do is you can withhold the vegetation and use only the insolation forcing and then see how the vegetation changes associated with the monsoonal response to insolation changes amplify the rainfall, temperature and so on and so forth. So, North Africa, it is a big story, right, because if you remember, now this place is complete desert. Sahara is a massive desert, Africa is poor and there is lots of problems associated with lack of water and so on. We will not get into the details, but somehow from being very green, now it is a complete desert. So, you need to understand what are the vegetation feedbacks. This is especially critical because in the 70s there was a nice study by a guy called Jules Charny from MIT that said people here are having so many cattle that they are grazing the land, and that grazing is actually making the desertification worse. This was a big kind of a news item because they said, wow, Africans are destroying their own environment and making their deserts even worse. But it turned out later on that actually the global warming and the ocean warming actually caused the worsening of the desert and the drought in the last 100 to 120 years. So, this shows you why we have to be careful when we detect a signal. So, we detected the signal that rainfall is decreasing over many decades in the Sahel region, which is the boundary between Sahara and the wet region, and then you have to figure out what is causing this signal you are detecting. So, the causes that you have to find are called attribution. So, attribution to the change, you detect a change and then you have to find the causes. So, that attribution you have to be very careful, because if you blame somebody and it turns out that if global warming is caused by Europeans and Americans over that period, then we should not be blaming the Africans. So, climate detection is oftentimes very easy, but attribution or making sure what is causing it, natural variability, human activity. If human activity, then whose human activity? This is very critical. This becomes critical as also as we go into the future, which we will come back to when we do more global warming. So, this is basically showing that the vegetation feedback is a good effect. So, it expanded. So, the rainfall was dropping off at about 15 degrees. With soil and vegetation feedback, you can see that the rainfall increased and it covered much larger part of northern Africa. This is not news in some sense. You might think back and say, of course, forests make climate better because they have humidity, local evapotranspiration, and they create a local microclimate. But then you have to worry about what happens if you remove only part of the forest or all of the forest and so on and so forth. But in general, you know that planting trees is a good thing. So there are some ideas on how that works, but we will not get into the details right now. So how has the insolation forcing worked? Basically, the precessional insolation going from the 9,000 years to the present has reached a minimum from the time where it started, and there is associated signatures in lake levels. So the weakening of the monsoon can be attributed to precessional changes over this time period with additional feedbacks from vegetation. This was essentially one of John Kutzbach's ideas, the insolation forcing of the monsoon. When he proposed it originally in the early 1980s, people were skeptical, but since then we have found many evidences like this which show that in fact there is a high correlation between insolation forcing and monsoonal response. So this is the lake level in some country in Africa, and you can see that there are complications there, basically because you have various hydrologic structures which determine how much water makes it to the lake, how much doesn't. There are thresholds of rain. If it doesn't rain enough, it can just evaporate and never make to the lake, and so on and so forth. Nonetheless, you can see that there is some similarity between the monsoon changes and the lake levels. So there is consistent data across various places and various lake levels and large scale patterns which can be reproduced from models that show that insolation forcing has definitely affected moisture supply and rainfall distribution, and has resulted in large scale greening and population movements and civilizations expanding and contracting over this time period. Let's look at another example at high latitudes of vegetation feedback. So in the model, again, you can just take insolation forcing and make a simulation and see how much warming would occur just because of changes in orbital forcing, and then you can add vegetation. Why do you care? Because when you change vegetation, for example, the northward expansion of a spruce forest which has a low albedo, which would amplify warming. So if you are warming and the spruce spreading north, it has low albedo, so it will increase energy absorption and enhance the warming and expand more. Whereas if you have something like the grasslands or tundra and so on, they have very different albedo. Tundra has much higher albedo than spruce. So tundra can have positive feedback in the other direction, where if you start cooling and tundra begins to expand, albedo goes up, more energy is lost, and the cooling is enhanced, so you can keep on expanding the tundra. So these kind of vegetation feedbacks are included in the model. So you do a simulation where vegetation feedbacks are not included, and you get this pattern of warming, and then you add vegetation feedbacks and see how the warming changes. So you can see here, just because of orbital forcing, winter, spring, summer and fall, the warming is strong in the winter, not so strong. In fact, there is a bit of cooling in the spring. Summer and fall again have warming. But if you have vegetation, then it is completely negating the insolation related cooling in the spring season and giving you amplified warming. So there are a lot of significant amplifications of warming because of vegetation feedbacks. So vegetation doesn't only affect the humidity levels, because remember, water vapor is also a very strong greenhouse gas, but it also affects albedo, and especially at high latitudes where the sun's rays are coming in and they are less energy is being intercepted per unit area. If you change albedo, you are going to reflect more sunlight and increase the energy deficit. Remember, in the tropics we have surplus energy, and at high latitudes we have deficit energy. So changing albedo at high latitudes, whether it's with snow and ice or with vegetation, you're going to have strong impacts on the climate and then the feedbacks. So it's an excellent example of how vegetation feedback works. So what is coming in the future in terms of insolation trends? So we are now going from 50,000 years ago to today to 50,000 years into the future. Again, Milankovitch has given us all the formulas and we can just use them. So here is what we can expect in terms of the precessional index. Remember, Sine omega here is the precession and epsilon is the ellipticity index. So, when we multiply them together, we get ellipticity modulated precession, which we called precessional index. That's there. So, from 10,000 years ago, we had a strong signature of precessional index and the tilt being in phase. 10,000 years from now, they will be completely out of phase. So, the net result will be that the insolation, summer insolation at 65 north, I cannot emphasize enough, summer insolation at 65 north is kind of critical because it can kick off the retreat and advance of glaciers, and that can start off the ice albedo feedback, and that can give us growing climate response. So, we had kind of highs in about, I don't know, 15,000 years ago, which started the deglaciation 20,000 years ago. 10,000 years ago, we had another maximum. Here it is given in terms of energy units. So, it is given in calories per centimeter squared per day. You can always convert them into watts per meter squared and back and forth and so on, but nonetheless we use different units for energy, it is still energy. And 10,000 years from now, you should come back to the present levels, and then somewhere around 13,000 years into the future, we will hit another maximum, and so on and so forth. So, this is what we have to keep in mind. So, if you are here today, 10,000 years ago we were started cooling. So, where were we headed, and how is global warming changing our evolution of the future climate? This is a very critical question. So, two ways to think about it, right. So, even if we do nothing, climate will change anyway because of orbital forcing, but it will change on its own time scale. But if we start tinkering with climate by changing greenhouse gases, carbon dioxide, albedo and ocean circulation and so on, glacier melting, then you can produce very rapid responses. As we saw in the younger Dryas, there are responses in the system that can occur on 3 to 10 year time scale, and there are responses that can occur on thousands of years of time scale. So, we have to just kind of understand all these feedbacks so that we know what is possible where, what are the tricky points in the system. Is it an El Nino response, is it the monsoon response, is it the vegetation response, is it the glacier response, or is it the feedback between them and so on. We have to be aware and see which one is the fastest possible response and what its impact will be. If monsoon suddenly dropped by 20–30%, on average it does not drop more than about 10%, but that is averaged over the whole nation. Even when the monsoon is considered normal by the parliament, Marathwada and Vidarbha can be having severe droughts, but that means there will be excess rain somewhere in Uttar Pradesh or Rajasthan or somewhere else, or maybe along the coast in Kerala and Maharashtra. So, how the rainfall is distributed itself also begins to become very important. So, what determines the distribution of the monsoon, and how will that distribution change as you change vegetation, as you change urbanization, as you change climate and so on and so forth. Those are the kind of things you have to remember in the context of the outside forcing. So, outside forcing will keep on happening, but we are doing something internally which is changing all the feedbacks. Those are the critical questions. Let us now try to put that in the long term context. We have looked at the tectonic timescale changes. Here we said there was a hothouse around 100 million years ago, and then we tinkered around, we kind of hung around, we had something called Eocene optimum. I did not say much about Paleocene, Eocene thermal maximum. Basically that was a sharp increase in temperature of almost 5 degrees in a very short time. You have to remember this is a very non-linear time scale here. So, it changed in 1 million or 2 million years. So, it is still much slower than global warming time scale. And there are some theories that it is related to a sudden release of methane that was buried in coastal cold waters under high pressure and so on. But The main thing we are focusing on was over the last 50 million years or so, we are in this cooling period, and we also mentioned that along the way the time scales that dominate the variability have changed. Sometimes there is a obliquity time scale of 41,000 years, and in the end we have the ellipticity time scale of 100,000 years, and I said they are not fully explained, so we don't know what are the causes that are taking the insolation forcing and producing these different time scales. We don't fully understand them, but in this focus on the glacial deglaciation time scale, we looked at a nice and systematic change in summer insolation, glacial melt, and then we looked at the hiccups due to sudden pulse of water being released and perturbing the thermohaline circulation and producing a rapid recooling called younger Dryas. It's called younger Dryas because the flower Dryas that was there in the glacial period had disappeared, and then it reappeared because the cooling reoccurred. That's why it's called younger Dryas. There is an older Dryas as well, which we didn't talk about in detail. And then we talked about the greening of Africa, increased monsoon at the end of deglaciation, which is related to orbital forcing. And we will look at much more detail since 9,000 years to now, what are the impacts of climate on civilization, and then each of the feedbacks we will try to put in the context of global warming. And we also looked at going into the future, what are the insolation forcing that is coming, and we have to now understand how that will interact with our activities and global warming. So, some of the take home points for this part of the course is that deglaciation is triggered by orbital forcing, summer insolation at 65 north, kind of a critical thing to remember. The melting of the glacier was hardly continuous. It had hiccups because every time the melting starts or the growing starts, there are changes in vegetation and monsoons and carbon dioxide and so on, which can produce local accelerations or local slowdowns in time of the freezing and the melting. Meltwater pulses perturbed the oceanic thermohaline circulation. This is some important feedback because Greenland is melting. What can that do to the thermohaline circulation and at what time scale? So, some evidence that rapid changes can happen in 3 to 10 year time scales. What will be the consequences? We need to understand those things. The global cooling initiated about 50 million years ago is the larger context under which global warming is happening. So, the insolation forcing, if we were headed into the next ice age, if we were in a 100,000 year time scale, are we still in a 100,000 year time scale and going back into an ice age after the end of the last deglaciation or the last glaciation, or is something changed, and is it changing because of global warming? Those are very difficult questions, but now we are more and more knowledge exists and the models are better and better at trying to figure this out. Global warming is occurring over the deglacial warming. So, locally speaking, the last ice age ended and we were deglaciating, and we have deglaciated even though there are glaciers over Antarctica and Greenland. And we know that 100 million years ago in the hothouse, there was no ice in the Arctic over Greenland and Antarctica. So, where is our next evolution? We need to figure that out. And how is the initiation of the next ice age affected by global warming? This I have repeated many times, but it is something to remember. Ice age, is it good for us? We don't know that, but at least we should be aware of what natural variability was trying to do and how we are changing it. If you look at the extinction of Neanderthals and so on, it's unclear. They were adapted to cold climate, but somehow they disappeared. Is it because of conflicts with Homo sapiens or diseases or something else? They seem to have a large enough brain. So, everything, if you want to be realistic, is that we are only around in this modern period. How has climate changed over this modern period, and what does it mean for our ability to deal with larger changes? That's kind of the question we'll come back to again and again when we look at millennial time scale, historic time scale, and global warming in the coming lectures. See you next time.